Hi, my students. Today we can discuss the concept of NMR and applications of NMR. As you know, NMR is a molecular absorption spectroscopy. Like any other types of spectroscopy, NMR is also an absorption spectroscopy. But it differs from the conventional IR UV visible spectroscopy in the respect that in NMR we are considering only the nucleus for the time being, and excitation of nucleus takes place upon interaction with the electromagnetic radiation. In this NMR, we are using electromagnetic radiation ranging from 60 to 800 megahertz, and we are keeping a magnetic force of a higher strength up to 8 Tesla. But in other types of spectroscopy, we are not keeping the molecular matter in an external magnetic field. So in nutshell, we can say, what is NMR? NMR is the resonance of the magnetic nucleus. Once again, it is the resonance of the magnetic nucleus. You know the term resonance. It is known as a condition under which two frequencies balance each other, or the two energies balance each other. And the magnetic means it has an inherent magnetic property. You may wonder how a nucleus is getting a magnetic property. A nucleus is getting a magnetic property due to the presence of the nucleons present inside the nucleus. The nucleons are protons and neutrons. They are quantum particles. And quantum particles do have inherent spin, and they are spinning in an imaginary axis. Am I right? As a result of spinning, it produces a magnetic field, and it has got definite magnetic moment. And the magnetic effect of the nucleus is taken into consideration, and we are keeping that magnetic nuclei in an applied magnetic field. So we are keeping the magnetic nucleus in an external magnetic field. Now just listen that all the atomic nuclei are not magnetic. All the atomic nuclei contain protons and neutrons, but they are not always magnetic. In order to become magnetic, the nucleus should have a resultant magnetic moment. In order to have a magnetic moment, it should have a net spin. Net spin is denoted by the letter capital I. And if I is equal to 0, it is said to be non-magnetic. And if I is not equal to 0, then it is said to be magnetic. And this I value can be half, or 3 by 2, or 5 by 2, or I can have values like 1, 2, 3, etc. If a magnetic nucleus is having a net magnetic moment due to the spin value or spin quantum number, half integral or odd integral, definitely the nucleus is having a magnetic property. So here we are considering the nucleus which is having a net magnetic property. And there are few examples. One is the hydrogen 1 isotope. Second one is carbon 13 isotope. Third one is nitrogen nitrogen 14 isotope. Next one is fluorine 19 isotope, and the next one is phosphorus 31 isotope. These are some of the examples of nuclei which are having magnetic spin or spin magnetic moment, which are generally called as NMR active. So these are the examples of NMR active. Now you can ask, sir, which of them are NMR inactive? NMR inactive, they are carbon 12 isotope. That is C12. This isotope, it is NMR inactive. And next one is fluorine 20. Fluorine 20. It is an NMR inactive isotope. So there are number of examples of NMR inactive. Majority of the nucleus are NMR inactive, and only very few isotopes become NMR active. Just remember that. And among the NMR active nuclei, the most prominent member, that is known as hydrogen, H1 isotope. And the nucleus of this hydrogen contains only one proton. Remember that. And it has got the highest value of the magnetic moment. And the magnetic moment value of this proton, that is calculated to be, the magnetic moment of this proton, that is calculated to be 2.777, and this is micro, and this is the value of the net magnetic moment of the proton, and that magnetic moment of the proton is far inferior to the magnetic moment generated by our Earth. So this has got a very low value, and among the NMR active nucleus, this is having the highest value. So most of the study of the NMR is carried out in proton, and hence NMR is generally called as NMR, that is generally called as H1 NMR. This is generally called as H1 NMR. This is also called as proton magnetic resonance, or PMR. And the concept of this PMR was put forward by Purcell and Bloch in 1949, and they were awarded Nobel Prize for this invention. And it revolutionized the scientific community, and it is widely used for the diagnostic purposes and also for the characteristic determination of the structure of the organic compounds. And remember that after carbon, the next prominent member in organic compound is hydrogen. So if one can take the spectrum, NMR spectrum of an organic compound, it is possible to identify the structure of the compounds more sharply. And we know IR spectroscopy gives only part of the information regarding the structure, and UV visible spectroscopy gives only part of the structure of the compounds. If you want to get the full structure of the compounds, you rely on this NMR, particularly H1 NMR. Right? Now we can pass on to the theory of NMR. Coming to the theory of NMR, we are considering first of all a naked proton. And usually the hydrogen contains a proton in the nucleus and an extra nuclear electrons in the shell. But here, for the time being, we are forgetting about the electron cloud present around the proton. Now this proton present in the nucleus of hydrogen, that is actually spinning in an imaginary axis. So this is the spin axis around which the proton is spinning, right? When the charged particle is spinning, around the proton, it produces a magnetic field, and that magnetic field is having a definite magnetic moment, and that magnetic moment, that is indicated by a magnetic moment vector. Now this is the direction of the applied magnetic field. So this represents both the spin axis and also the direction of the applied magnetic field. This is the direction of the applied magnetic field. And what is this one? This is the direction of the magnetic moment vector of the proton due to spinning. So in presence of an applied magnetic field, what will happen? The magnetic moment vector will align with the direction of the applied magnetic field, but the vector will be tilted. The vector will be tilted to 60 degrees. So this is the position of the magnetic moment vector. And that magnetic moment vector starts moving around the spin axis. There the magnetic moment vector is not at all stationary. It is moving around the spin axis or the direction of the applied magnetic field. The continuous movement of the magnetic moment vector around the spin axis, that is known as the precessional movement. Once again, the continuous movement of the vector around the spin axis is called as the precessional movement, and it occurs with a particular frequency, and that frequency is called as the Larmor frequency. That is known as the Larmor frequency. And that Larmor frequency nu, that is equal to gamma into G divided by 2 pi. Sometimes G may be replaced by B. B is the strength of the applied magnetic field. B or B0, that is the strength of the applied magnetic field. And here this gamma is a constant, and that is known as the gyromagnetic ratio. And this gyromagnetic ratio is a constant quantity. For every magnetic nucleus, it has got a constant gyromagnetic ratio. And that gyromagnetic ratio for the proton, that is equal to gyromagnetic ratio, that is equal to 267. For the proton, it is equal to 267.5. This is the value of the gyromagnetic ratio, and this is this much radians per Tesla. So this is the gyromagnetic ratio of the proton. And C13, that is another NMR active, it has got another gyromagnetic ratio. Therefore, the Larmor frequency nu, that is equal to gamma into B0 divided by 2 pi. So this equation is very important. And if you know the value of the gamma, you can calculate the frequency of radiation required for the excitation of the nucleus under a magnetic field B0. So if you know the value of the B0, and if you know the value of the value of the gyromagnetic ratio, now you can calculate the value of what? Value of the frequency of radiation required for the excitation of the nucleus. We can also compare the frequencies. For the resonance using this expression. And ultimately we can say the frequency for the resonance absorption, that is proportional to gamma, nu proportional to gamma, when B is kept as a constant. Nu proportional to gamma. Remember that. And this way the proton is spinning around the magnetic moment vector of the proton is spinning around the spin axis, applied direction of the magnetic field or the spin axis. Both are the same in this case. And here we are going to give an electromagnetic radiation. When we are giving electromagnetic radiation ranging between 60 to 800 megahertz, the radiation will be absorbed by the proton. And in order to absorb the radiation, there should be a condition. What is the condition? The condition is that two frequencies should balance each other. Now what are the two frequencies? One is the Larmor frequency. You know what is meant by Larmor frequency. That is, Larmor frequency is the frequency of the magnetic moment vector of the proton that is moving around the spin axis. That is the frequency of the magnetic moment vector around the spin axis. That is the Larmor frequency. And what is the second nu? Nu is the frequency of the interacting radiation. When these two frequencies balance each other, the condition is said to be what? The condition is said to be resonance. So what is the resonance? Resonance is the same. It means it is the same. Same means the two frequencies should have the same value. That means energy of these two that match each other. Energy of the magnetic moment vector and also energy of this radiation, they balance each other. And when the condition is reached, when that resonant condition is reached, what will happen? The proton will absorb the radiation. The proton will absorb the radiation as a result of the resonant absorption. That property is known as the resonant absorption. As a result of the absorption of that electromagnetic radiation belonging to the radio waves, the magnetic moment vector, what will happen to the magnetic moment vector? Magnetic moment vector will be turning upside down. The magnetic moment vector will be turning upside down and in the opposite direction, where the magnetic moment vector is getting aligned against the direction of the applied magnetic field. And the process of transferring the magnetic moment vector from this side to the second side, that means it is earlierly it was aligning with, but now it is aligning against. So the transition of the magnetic moment vector from with position to the against position, that is known as the spin flipping. In order to flip the spin, the proton requires some amount of energy, and that energy is given by, that is imparted by this radio frequency radiation. And when that magnetic moment vector is turning upside down, see that magnetic moment vector again starts moving around the spin axis. Again it precedes with a particular frequency. Now this is the higher energy state, this is the higher energy state, and this is the lower energy state. This is the lower energy state. So transition from the lower energy to the higher energy takes place. Now from this higher energy state, the proton can revert back to the normal state by releasing energy. That process is known as relaxation. So what is meant by relaxation? Relaxation is the process by which the magnetic moment vector will be going back to the normal position. How we can go back to the normal position? The magnetic moment vector can go back to the normal position by releasing the excess energy. How the proton can release the excess energy? There are two mechanisms. The two mechanisms are said to be the spin-spin interaction and also the spin lattice relaxation. Due to these two mechanisms, the proton release the excess energy and the magnetic moment vector will go back to the lower level, and that process continues, the absorption continues. And in another way we can say the proton, the net spin value I equal to half. Okay, if the net spin value equal to half, there can be 2 into I plus 1 spin energy levels according to quantum mechanics. So there are 2 into I plus 1 spin energy levels, that is equal to 2 into half plus 1. 2 into half plus 1 equal to what? 2 into half plus 1 equal to 2. So there are 2 spin energy levels in every proton. Now in organic compound there are present cohorts and cohorts of protons. Here we are considering only one proton. So as far as a proton is concerned, it has got 2 spin energy levels. These are the 2 spin energy levels, right? We can represent the 2 spin energy levels like this. So how many spin energy level are possible for a nucleus, for a magnetic nucleus? That is 2 into I plus 1. 2 into I plus 1. 2 into I plus 1, where what is I? I is the total spin. Suppose I equal to 1. If I equal to 1, 2 into 1 plus 1 equal to 3. There are 3 energy levels. Suppose N is equal to 3 by 2. when I equal to 3 by 2, 2 into 3 by 2 plus 1, 2 into 3 by 2 plus 1 equal to 4. 4 energy levels are possible. But fortunately, our proton that is having only 2 energy level, because I is equal to only half. I value is only half, and hence there are only 2 energy levels. The 2 energy levels, they are coined, they are named as alpha level and also the beta level. What are they? They are the alpha level and beta level. Now they are having the same energy, and we know the energy levels which are having the same energy, they are called as degenerate. They are called as degenerate. Therefore, the alpha level and beta level, they are degenerate levels. Now, there present no external magnetic field. Now, we are going to keep the 2 levels in an external magnetic field. When you keep the 2 levels in an external magnetic field, what will happen? The 2 levels got separated. The 2 levels got separated. Now, this becomes the beta level, this becomes the alpha level. The extent of separation, that depends on the strength of the magnetic field. Higher the strength, more will be the separation. Now again we are increasing the strength of the magnetic field. When you are again increasing the strength of the magnetic field, the 2 levels got separated further. So this is the position of the 2 levels, right? Now this becomes the alpha level, this becomes the beta level, right? Now proton is in the lower energy level. This is the proton, and this is in the lower energy level. This is the spin axis. This also be the same as that of the direction of the applied magnetic field, and this is the direction of the magnetic moment vector of our proton, and that magnetic moment vector is moving around the spin axis and also moving around the direction of the applied magnetic field with a particular frequency. I told you earlier, that is Larmor frequency. In this condition, we are giving a radio frequency radiation. When we are giving a radio frequency radiation, then the proton will absorb the radiation. When the proton absorbs the radiation, that absorption occurs only under resonance condition. We know resonance is the condition under which the 2 frequencies balance each other. As a result of the absorption of the radiation, the proton jumps to the higher energy level. So this is the position of the proton after excitation. Now this is the direction of the applied magnetic field. There is no change. That is nothing but the spin axis also. But see the direction of the magnetic moment vector of the proton. The magnetic moment vector of the proton will be tilted. So that process is known as, spin flipping. Therefore, we are measuring the energy needed for the spin flipping, and that energy can be calculated using the NMR spectrometer. Now, NMR spectrometer measures the frequency or the energy needed for the spin flipping and produces a plot between what? Between the intensity and also the energy or the frequency of the radiation needed for that spin flipping. Now we can also calculate the strength of the magnetic field required for the resonance absorption. We can also calculate the strength of the magnetic field required for the resonant absorption. So in the y-axis there present only one parameter, that is the intensity of the signal, and in the x-axis we can have either the frequency or the field strength. So we want to keep one as constant. Now we can keep gamma as the frequency as constant. When frequency is kept as constant, when the frequency of the radiation giving is kept as a constant, we are calling that technology as field sweep method. And if field is kept as a constant, if the magnetic field is kept as a constant and frequency is varying, it is known as the frequency sweep method. But when you consider the 2 methods, the field sweep method is far better. So from the instrumental point of view, the instrument can measure the magnetic field required for resonance easily, and hence we are giving one and the same radiation to the nucleus and varying the magnetic field. In that way we are taking the spectrum, and that spectrum will appear as signals like this. From this intensity, from the position, etc., we are interpreting the structure of the molecule. We are locating the cancerous cells in organic body. And we know there are two levels in the proton, in a magnetic proton. The two levels are the alpha level and also the beta level, we know. And the energy of the alpha level is A alpha, energy of the beta level is E beta. And the E alpha level, the energy of the E alpha level, that is equal to minus half into Gn, Bn, B0. This is the energy of the lower level, alpha level. That is, minus represents the quantum number, Gn and Bn, they are constant, they are called as nuclear G factor. Nuclear G factor and Bohr magnetone, they are constant for the nucleus, and the nuclear G factor is equal to 5.8. Nuclear G factor, Gn value equal to 5.587, 5.587, and Bn, that is also constant, Bohr magnetone, and that Bohr magnetone, that is equal to 9.27 into 9.27 into 10 raised to minus 24. See the lower value, joules per Tesla, joules per Tesla. So E alpha level, that is having the energy minus G and B and B0. What is B0? B0 is the strength of the applied magnetic field. B0 can be represented in terms of Tesla or in terms of Gauss. And energy of the beta level, that is equal to half into Gn into Bn into B0 into B0. Now the separation, the difference between the two energy levels, E alpha and beta, that is delta E, equal to higher energy minus lower energy, that is E beta minus E alpha. E beta minus E alpha equal to half Gn Bn B0 minus of minus Gn Bn B0. So what you are getting? E beta minus E alpha, that is equal to Gn Bn B0. So Gn and Bn are constant. We know delta E, that is equal to, or that is proportional to the strength of the applied magnetic field. Therefore the separation can be manipulated by changing the magnetic field. So the resolution of the spectrum can be improved by changing the magnetic field, because the energy level separation delta E, that is proportional to the strength of the magnetic field. Again we know delta E proportional to B0, delta E is equal to h nu. So we can also write delta E proportional to nu also. Therefore the final equation is delta E proportional to B0 proportional to nu. Just by heart this expression, the separation between the two energy levels delta E proportional to B0, that is proportional to frequency of the radiation, and the field strength and frequency, they are directly related to each other. Right? Now we can pass on to the next session. The next session is the chemical shift. So in the next video I shall say more about the chemical shift and also the spin-spin coupling. Only after that you can interpret a spectrum. Right?